It's going to serve as your first organic chemistry classes. So, my name is Huiling Shao. I'll be your instructor for this entire quarter. And let's just go over the syllabus first. And this is lecture 1. So we will be talking about the syllabus. And then we will also be talking about some of the reviews on previous chemistry knowledge you learned in 14A and 14B. All right, getting started. I'll be highlighting some important information in the syllabus. Before we get started, people in the back, can you hear me all right? Okay, sounds good. So I'll just go over the syllabus. We'll take about 10 minutes to highlight some important things you need to know. I also posted a syllabus quiz. It's an extra credit item on Canvas. So I give you all the way until the end of this week, which is Sunday night, to finish that syllabus quiz. So go check that out, read the syllabus, and get that 4 extra credits. That's only if you need it. If you don't want it, that's also okay. All right, so 14C. Just go over my name. This is my email address. You can also find it on Canvas. So the email is always the best way to contact me. You can also send me a message through Canvas inbox or mailbox, whatever. So email or Canvas message, these are the 2 best ways to approach me. I'm typically very fast with replying emails, but again, I have 700 students, so if I'm being late for like 1 or 2 days, please be patient with me. I'm normally very quick with my email. Office hours, this is a tentative schedule, which is Thursday, every Thursday from 10 a.m. to noon. That's the office hour for both my sections. Right now, I'm not 100% sure if the room is big enough, but if it's not, we might be changing to a bigger room. So I'm just going to leave the 2077E Young Hall for now. We'll just meet in 2077 for my office hour. It's subject to change. If there's a change, I'll post it on Canvas as well. Class meeting time, you're already here. You know when our class is. And for this class, attendance is not mandatory. That means if you want to just watch the video later on, it's also okay. So this class is part of the brewing recording, so you can find the recording of the lecture both via the brewing recording or brewing cast. That's on Canvas. I'll also post my own version of the recording because the audio quality of the brewing cast sometimes can be shaking. So I'll post my own recording on YouTube, so you can choose whatever recording you want to watch, and it will be available online. So naturally, I'll expect less attendance from next lecture, but it's okay. Anyway, so that's a recording. So if you have like other emergency, you can't attend the class, just do make sure you watch the recording on time. Like, do not wait until the night before the midterm exam and you start watching the recording. It doesn't work that way. I promise you that. So stay on top of your game. It's your own course. It's your own grade. You take responsibility of your own learning curve. All right, TAs. We have lots of TAs working with me for discussion sessions. So the discussion sessions are a very important part of your learning experience. So it happens every week, including this week. So you will have discussion session this week, starting Tuesday, depending on which section you are. You will be able to find your TA's contact information and also the assignment. The assignment might be changing, but the TA contact information is posted there. And you can find that on the syllabus. I'll keep the syllabus on the Canvas to be updated as soon as possible if anything is changing. So that's a TA assignment. You'll also be helped with Learning Assistant. Some of you might already be familiar with Learning Assistant in your 14A and B series. They will be present in your discussion session to answer your questions and to work with you together. They're just undergrad students who took the class in like 1 or 2 quarters before. So Learning Assistant, they're all like great resources if you need help. All right, course materials. So I don't have any required course material for this class. Like if you don't buy the textbook, it's okay. You can use our lecture note as your reference. But it's highly recommended. It gives you extra like practice problems or like information you need that's a textbook requirement. It's also highly recommended that you have a molecular kit. We'll use molecular kit when we start to talk about structures, especially when we talk about conformation, strand, and those stereochemistry. A molecular kit is highly useful for those regards. Highly recommended, but if you don't have it, you might be able to if you don't have it, you might be able to borrow it from your friend, which is also fine. Or like you can have 2 or 3 people sharing the same molecular kit. That's also fine. Sometimes we only need a center atom and maybe 4 other atoms surrounding it. Since my class is recorded, so you probably need a laptop, tablet, or any kind of electric devices just to read it. I'll skip the inclusive access part, and here comes the part people actually care. So the grading scheme. So we have several things for this class. The first thing is the collaborative discussion worksheet. So except week 1 and week 10, you will have a total of 8 discussion worksheets. So these discussion worksheets, you'll work on it together in your discussion session with your TA and LA. So that's supposed to be exam styled, more like comprehensive type of question in your discussion worksheet. But you can work together with your friend and with TA in your discussion session. You will not be able to work with your friend in the exam though. But those are very important part of your grade. So a total of 24% of your grade will come from your discussion worksheet. And then for every topic, I'll post a Canvas assignment. You should be able to see the Canvas assignment for our topic 1, which is our first chapter on Canvas already. It's a multiple choice style or matching style question on Canvas. So that accounts for 16% of your total grade. So if I'm counting it correctly, these 2 are 40% of your grade. It's like collaborative. You can work with anyone you like. You can work with any resource you like. So these 40% of the grade are just like free points if you work on it. So my suggestion is, again, stay on top of your game. Work on it as soon as possible. Do not delay it until the last minute. And these are just like free points. Just study for it. You can ask any question. You can get any help you like. On top of those 40%, we have 60% rest of the course graded based on your exams. We'll have 2 midterm exams and 1 final exam. So you can see the schedule of those exams in our class schedule. I'll also offer about 30 points, which is like 3% of your grade as extra credits. So these extra credits will be calculated at the end of the quarter. The first extra credit item, again, it's the survey for the syllabus. So take a look at the syllabus and get that for extra credit. All right, so that's the course policy. Yes? Oh, I might have got it wrong. I'll have to double check. So these are accurate. I might have copied from my previous class. Thank you for pointing that out. Okay. And the letter grade policy, it's pretty standard UCLA policy. Again, 40% of your grade are free point. You only need to get another, well, if you're just looking for passing, you only need 20% of the grade from your exam. But I'm sure you're here to get an A, not to just pass the course. Exam policy. So organic chemistry are typically have lots of memorization. But I don't like the rigid memorization some people might require. So for my course, your exam will be open book, open note. But there's a hint here. Because it's open book, open note, your question will be more comprehensive. You'll see that in your discussion worksheet. So the ability of go to your note and find that correct equation, find that correct concept to use will become critical. So it doesn't work if you're studying at the exam, even if it's open book, open note. So again, do study for your material, get familiar with material, know which part of the lecture note you should be referring to, and don't spend too much time just memorizing all the terminologies or the nomenclatures. Those are less important in this class. The class is not curved, So you'll read it, but at the end of the quarter, if our class average is below B minus, which never happened before, I will pop everybody's grade up if the average is below B minus. But other than that, the class is not curved. I'll skip the regrade policy and the missed exam and quizzes. You can read it later, and also the technical requirement and COVID policy. For the COVID policy, it's just one word: stay home if you're not feeling well. I mean, all the lectures are recorded, and there is no point. Academic integrity, that part I'll also skim over, but you should, like, again, follow the honor code. It's your own responsibility, it's your own learning. Okay, and the last part is our course schedule. This also serves as a quick overview of this entire course. So we'll have 8 different topics for this entire quarter. The first week, we're talking about chapter 1 of the textbook. And this part is more or less a review if you're taking 14A and B. I'm not sure how, like, what material are being covered. So I'm just going to go over the review on 2 topics. What is an atom and what is a chemical bond? So for the chemical bond, we'll be talking about 2 different types of bonding theory, the classical bonding theory as well as the quantum bonding theory. Topic 2 are just very fundamental things of organic chemistry. You hear the speaking of organic chemistry being a language. So our chapter 2 will be talking about the basic grammar and also vocabulary of our organic chemistry. What we're talking about when we're saying kinetic and thermodynamic. What we're talking about when we're saying reaction mechanism and functional groups and so on. So this part is to set the canvas ready for organic chemistry so that in the future when I'm saying, hey, this is an acetate group, you know what I'm talking about. You have the structure in the back of your mind. Chapter 5 will briefly touch on stereochemistry. We'll come back to stereochemistry when we talk about carbohydrate, which is biomolecule later on. And that 3 topics goes to our midterm 1. We'll have the basic review on what is an atom, what is a chemical bond, and we'll be talking about basic vocabularies of organic chemistry and also stereochemistry before midterm 1. For midterm 2, we're focusing on spectroscopy. So one important thing in organic chemistry is how do we know the structure? How do we know what kind of molecule we have? Like, we don't have microscopic vision on the molecule, but using spectroscopy method like NMR, IR, and also mass spectrometry, you can get information about what the structure of an organic molecule looks like. And with that information in hand, you can then know, like, what kind of reaction is taking place and derive all the organic chemistry based on it. So these are spectroscopy topics, and we'll spend pretty much all our lectures 13 to 20 talking about spectroscopy. And at the end, in chapter 24 and 26, we'll be talking about some biomolecules. And these are particularly interested if you're aiming for a biochemistry major or you're aiming for a pre-med career. We'll also merge in some topics regarding like non-covalent interactions, hydrogen bonding into these biomolecule topics as well. All right. Do we have a question before we move on to the actual material of today? Yes. Right, so the question is, the exam is open book, open notes. If you're using your tablet, you cannot use any internet. So if you're taking note on your tablet, you can use your tablet just to look at your note. You're not supposed to connect to internet. All right, any other question? Yes?
Is it a take-home?
The exam is not a take-home. It's going to be in person. Half of you will take the exam in this classroom. Half of you will be in a different room. I'll post that when the time comes. Okay. I'll stay out. I mean, I can't stay outside because there's another section coming up. But I'll be around for questions if you have any. All right. So let's get started for our today's lecture. Just quickly, before we get started, on Canvas, you'll see two sets of lecture notes. One of them is called annotated. One of them is called blank. So in this class, I will always start from what I call a blank note, and then in the class, we'll work on these blank notes together. Whatever I write on my notes in class will be included in the annotated version of the lecture notes. So that means in the class, please spend some time just looking at the lecture notes when we're working on it. Spend less time just writing down everything on the PowerPoint, because it will be available for you on the annotated note. All right, so pay more attention to what we're talking about and pay more attention to thinking about the actual knowledge you come here to learn, and pay less attention to just copy down everything in class. Okay, so for today, we have 3 different topics. The first one, overview of organic chemistry. This one we just did. We will be talking about first, what are the basic vocabulary of organic chemistry, what are the chemical bonds we're talking about, and then we'll also talk about spectroscopy, like how do we know a molecule has certain structure, and the end we'll be talking about biomolecules. So that's the structure of our course today. We'll pay less attention to actual organic chemistry reactions. You'll see that in 14D. So 14C is like preparing you ready to write down those complicated chemical equations. So that's our overview. This is already done. That's in our textbook 1-1. And now let's move on to talk about atomic structures and molecular structures. That's in 1-6 and 1-9. All right, atomic structures. We'll touch a little bit on quantum mechanics. You also did that in your 14A classes. So what are atomic structures? What is an atom when we're talking about it? So what we're having here, an atom that's a microscopic, it's a very small subject. So naturally, we need to use quantum mechanics to describe the electronic property of an atom. So in one sentence, when using the quantum mechanics, we're solving the Schrödinger equation to get a wave function. And that wave function tells you everything. So the Schrödinger equation has a general form of a Hamiltonian acting on a wave function, gives you energy and a wave function. We're not solving it here today, but just so you know. And the wave function phi, it tells you everything. So for example, if you want energy, you use the correct question, which is the Hamiltonian. That's the question you ask. And the wave function acts as an oracle to give you energy. All right, so your wave function is like an oracle. You need to find the correct question to ask. Or if you want to have probability. Or in another word, now we have a hydrogen atom where my electron density is. So the probability in finding an electron somewhere in space, that probability is given by the wave function absolute value squared. In organic chemistry, we'll use the word atomic orbital a lot. So what does that atomic orbital mean? It means when we're solving the Schrödinger equation for a 1 electron hydrogen-like atom, so that's hydrogen or helium plus, lithium 2 plus, etc. As long as it only have 1 electron, we can solve it exactly. We can find the exact analytical solution of the Schrödinger equation. And these solutions are my exact 1 electron wave functions. And they are equivalent to atomic orbitals. All right, so what that means is atomic orbitals, when we're saying it, they are solved mathematical wave functions for the Schrödinger equation. So atomic orbitals is not the electrons circulating the nuclei. That's a common misunderstanding. This is a take-home message. I hope we're on the same page. Atomic orbitals are one electron wave functions. They are mathematical wave functions. In quantum mechanics, we have several quantum numbers to describe a specific wave function or a specific atomic orbital. So I'm just going to show you the three quantum number here. So quantum number is connected to quantized physical properties. The first one and the most important one is the principal quantum number. It's associated with energy. You should be able, this equation, you probably have seen it before when you're working on the Bohr model. It gives you the energy level of your atomic spectrum for any hydrogen-like atoms. The angular momentum quantum number L is our second quantum number. L tells you what's the shape of your atomic orbital, or what does your atomic orbital looks like, how to sketch your atomic orbital. And then, in this case, in organic chemistry, when we say L equals to 0, we're saying there's an s orbital. When L equals to 1, that's a p orbital. And when L equals to 2, that's a d orbital. Since we're talking about organic chemistry, so s and p orbitals are more important in this class. And then we also have the magnetic quantum number. So here is the selection rule for the magnetic quantum number m. It goes from negative L plus 1, all the way to positive L. So I want to pause here and ask you to think about a quick question. There only exists 3 p atomic orbitals. Can you think about it, why that's the case? Yes?
There's only 2 electrons in each orbital, so if you were to have 4, that would be 8. That's not okay.
Yes and no. So it actually works the other way. When we're saying there are 3 p atomic orbitals, what we're saying is that p atomic orbitals, that's equivalent to, say, L equals to 1. So your angular momentum quantum number L equals to 1 for p atomic orbitals. But for the magnetic quantum number, here is the selection rule. Your m can only take 3 different values from negative L, which is negative 1, 0, and 1. So because when L equals to 1, your m can only take 3 different values. So that's where that 3p atomic orbital comes from. And think about it, why they only have 5 d atomic orbital. It's the same logic. For d atomic orbitals, you only have L equals to 2. So m can take 5 different values. All right. And let's look at some of the atomic orbitals since we're talking about it. Again, atomic orbitals, they're just the solved electronic wave function when we're solving the Schrodinger equation for any one electron systems. So if you have a piece of paper, we can draw that together. You definitely need to know how to draw these atomic orbitals. 1s, that's L equals to 0. That's a spherical shaped. And we don't have any angular nodes. All right, spherical shaped, that's the 1s atomic orbital. We do not have any 1p atomic orbital because for n equals to 1, your L can only be 0. But we can have 2p atomic orbitals. So what these 2p atomic orbitals look like? Here we have the Cartesian coordinates. So let's just draw it. We'll draw the pz first. And px. And py. In all of our p atomic orbital, there exists an angular node. So what is a node? Again, this is a quick review. When we're saying there exists a node in your atomic orbital, what we're saying is whenever your wave function reach that point, reach that node plane, your wave function changes sign. All right, so that's what that shading comes from. It is a wave. If you imagine like a sine wave, so I'm just going to quickly draw it. If you imagine like a sine wave, what we have here, that's the positive region, that's the negative region. So at the node, your wave is changing sign. So if I color code all my positive region to be shaded, then the negative part is unshaded. So when we're talking about a node, it basically is saying your wave function is changing sign. And if you remember, when we're saying the angular node, your wave function is changing sign, or your wave function is about 0. Or it means is you have low electron density region. All right, you have less electron density around that node plane. All right, so that's a quick review on the question, what is an atom? And we were talking about one electron atom, like a hydrogen atom. But when we're working with multi-electron atoms, you have multiple atomic orbitals you need to talk about. So when we're moving on to talk about multiple electron atoms and with multiple atomic orbitals, here are the fundamentals of the electronic structure of any atom you have. So first of all, the combination of the first 3 quantum number, N, L, and M, give you different atomic orbitals. So remember, when we're talking about the 2p atomic orbital, what we have is N equals to 2, L equals to 1, and then M equals to -1, 0, or 1. So that's why we have 3 2p atomic orbitals. And then you can put electrons into those atomic orbitals. So again, one common misunderstanding here is atomic orbitals is always available. Even if we're talking about hydrogen, has 1s, 2s, 2p, 3s, 3p, it's always there. Whether or not it has electrons in there, that's a different topic. So you write out the atomic orbitals first, and then you put electrons in there. When putting in the electrons into the atomic orbitals, we have 3 different rules we need to follow. First rule, the low energy atomic orbitals will get filled before the high energy atomic orbitals. So you start from the lowest energy atomic orbital, you fill it up. The second rule is no 2 electrons in the same atom can have the same set of all 4 quantum number. So that means you need to either, each atomic orbital can only take 2 electrons, one spin up, one spin down. At the end, we also have the Hund's rule, means when electrons enter a degenerated atomic orbital, when we say degenerate, we just mean these atomic orbitals have the same energy level. They will enter each atomic orbital singly occupied. So if it doesn't make too much sense to you, we'll do an example together. Let me just write down. Okay. So let's do 2 examples together regarding the electron configuration. So here are the 3 rules we have. Let's think about carbon and oxygen. We'll do carbon first. So for carbon, we have Z equals to 6. So Z, that's our atomic number. You read the periodic table to find out the atomic number of that atom. And we have the energy level diagram. What we have is 1s, that's the lowest lying, and then 2s and 2p. When we say degenerate, we're just saying these 2p atomic orbital have the same energy level. So when we put the electrons in, we have a total of 6 electrons. The way we do it is, again, we put it in from bottom up. So 1, 2, 3, 4, 5, 6. All right, we start from the lowest energy atomic orbital, we build it up. Each atomic orbital holds 2 electrons, one spin up, one spin down. And at the end, for the Hunt rule, whenever your electron enters degenerated atomic orbital, they went singly occupied before they pair up, just to avoid electron pairing energy. So that's a carbon example. On the right-hand side, let's do the oxygen together. So for oxygen, we have Z equals to 8. So we have a total of 8 electrons. Again, the same logic, we put it in. 1, 2, 3, 4, 5, 6, 7, 8. Or when we write the electron configuration out for carbon and oxygen, so for carbon, you have 1s2, 2s2, 2p2. Or that is equivalent to say it is helium, 2s2, 2p2. So that 1s2 is the electron configuration of noble gas helium. For oxygen, it's the same idea. You can write it as helium, 2s2, 2p4. So that's writing the electron configuration. All right. So I'll pause here for any questions regarding atomic structures. It should act as a quick review, but if you have any questions, now is the time. Okay, go. Okay. Wow.
Can you go over the wave function changing sign again?
Okay, so the wave function changing sign. I know my drawing on the board is not super clear. When we say a wave function, let's just imagine this is a sine function.
Yeah.
So here, that's 0. That's the x-axis. And you can imagine a wave function going like this. All right, that's a sine function. So let me just shade everything that's positive and unshade everything that's not positive. So when there is a node, it basically said your wave function is changing sign at that node. So here, the shaded parts are all the positive part of your sine wave. The unshaded part is all the negative part of your sine wave. And at the node, your wave equals to 0, which in this case, your sine wave equals to 0. But in the atomic orbital, that's the same idea. Whenever you have a wave that's passing a node, it changes sign.
Like it's rotating?
The way to think about it is not rotating. It's just, for example, this is a traveling wave. This is a plane wave that's just keep going, right? Every time it passes that node, it changes sign from the shaded to unshaded, alternating. Okay. Any other questions? All right, sounds good. So let's move on to our next topic, which is molecular structures. So again, these are the very, very basic vocabulary of chemistry. What we're talking about when we're saying, hey, here is a molecule, we have so many different formulas people can use to describe a specific molecule. We'll start from the most simple one, which are empirical formulas. That gives you the relative ratio of atoms. So for example, if I have an empirical formula of CH2O, what that means is the element carbon and the element hydrogen and the element oxygen in this molecule equals to 1 to 2 to 1. Or it just tells you the ratio of different elements in that specific substance. So that's the most simple one. Molecular formula gives you a little bit more information. It specifies the number of atoms in just one single molecule. So for example, when we're saying the molecular formula of benzene is C6H6, What that means is effectively saying each benzene molecule contains 6 carbon atoms and 6 hydrogen atoms. All right, so molecular formula tells you in this one specific benzene molecule contains 8 carbon atoms and 8 hydrogen atoms. As a quick question here, since we're talking about it, what's the empirical formula of benzene? Remember, empirical formula gives you the ratio of element in that substance. Yeah, that's just CH, right? So the ratio of carbon and hydrogen element in benzene is just CH. So the empirical formula is just CH. All right. I left a question here just regarding the molecular formula. I'm using the hemoglobin here as an example. Again, you'll find the answer of this practice problem in the annotated note. It basically is a practice saying like, hey, here's the molecular formula, how to write the empirical formula out of it, how to calculate the molecular weight, the percentage mole, percentage weight of different elements in that specific molecule. So you can practice yourself and check your answer with your annotated notes. All right. So now let's move on to something new. So everything I talked about, I assume you already learned it. They should serve as a quick review. And now we're working into the world of organic molecules. On top of empirical formula and molecular formula, the structures of your organic molecule is essential when we're talking about their chemical properties. So there are several different ways we can draw our organic molecules. So for example, I said skipped Kulak, but that's lying. We actually need to talk about it. So for example, we're using vinyl chloride here. Vinyl chloride, that's the name of the organic molecule. It has the molecular formula of C2H3Cl. What that means is each molecule of vinyl chloride has 2 atoms of carbon, 3 atoms of hydrogen, and 1 atom of chloride. So the different ways we can draw it, we have the condensed formula, where you have the CH2 double bonded to CH, and the chloride is also bonded to CH. So that's called a condensed formula. You're just writing it out in a single line. More often, we will be using the bond line formula, which is drawn here. In the bond line formula, we ignore or we omit all hydrogen atoms in that sketching. And we don't show the carbon atom. We just show, for example, here, in the actual write-out, what we have is hydrogen bonded to carbon, to hydrogen, and to carbon, hydrogen, and chloride. So this is the Kula formula for vinyl chloride. But in the bond line formula, what we have are carbon atoms have this zigzag frame, means they actually represent the actual molecular geometry that's surrounding that carbon atom. And we do not show our hydrogen atom when drawing the zigzag frame. Now we want to pause here and just think about it. Why do we need that zigzag frame? We'll use 2 different molecules here as an example. When we're drawing that zigzag frame, what we have is your carbon atom, for example, the methane, actually has a tetrahedral geometry around it. So again, that's a quick review of tetrahedral geometry. You have 4 things around it. The tetrahedral is the best way to put it so that your electron pairs are most distant from each other. So for example, methane, you will have a tetrahedral geometry where these 3 atoms are on the same plane of my drawing pad. And then you will have 1 hydrogen coming out from the plane and 1 hydrogen inside the plane. I recommend you use a molecular kit to just build it and see why that's a zigzag form. So that's just a methane. But when we're drawing it into the three-dimensional, for example, if we have propane, again, all of the carbon here are are tetrahedral geometry. So naturally, we will have all of them having this zigzag form. All right, so whenever we draw a wedged line, means that atom or that group is pointing out towards you. Whenever you draw a dashed line, it's going into the paper away from you. And these regular lines representing they are on the same plane here. So what's the bond line formula for propane here? If we draw it in the bond line formula, that's how we do it. We ignore all the hydrogen, and each carbon is at the point here. So each of these points in your line, bond line formula is a carbon atom. So you'll see lots of practice exam for these bond line formulas in your textbook, and we'll use that in our future discussion a lot. All right. The last topic of today is constitutional isomers. So, as we just showed before, organic molecules, the structure of organic molecules or the 3D orientation of your organic molecule is very important. And molecules with the same molecular formula means that they have the same number of carbon hydrogen atom in that molecule. They can have different connectivity. And these constitutional isomers are defined when molecules have the same molecular formula but different connectivity. We'll use the C5H12, which is propane, as an example here. On the left-hand side, we'll draw the bond line formula. And then on the middle, we'll draw just write out the name. And then at the end, we'll have the conventional name, IUPAC name. So this one has 3 different types of constitutional isomers. You can have 1, 2, 3, 4, 5. So that's 5 carbon. That's the linear version. Or you can also write it as CH3, CH2, 3, CH3. And that's our linear pentane. You can also have isopentane, means you have some branching in your drawing. So that means instead of having all linear, we can have one branching here. Or the way to do it is write it out as CH3. Now you have 2 different CH3 and just one CH2 connecting to another CH3. So that's our isopentane. We can also have our neopentane, where you have the same carbon in the middle that's connecting to 4 methyl group at the end, or CH3 group at the end. Here we have our CH3, 4 of them, C. That's our neopentane. Again, just different connectivity. You have the same molecular formula. Yes?
For the second one, for the molecular formula, missing a pH between the CH3 and CH2.
Sorry, what's the question here?
So like is the for the molecule?
Oh yeah, that's right. Thank you. Oh, that a reminder, we have 5 minutes left. So I'll do one more example here for the constitutional isomers. You can also have constitutional isomers when you have heteroatoms. When we say heteroatoms, we're saying now instead of just carbon and hydrogen, you can have oxygen, nitrogen, sulfur, etc. in your molecule. So here for C2H6O, so that's the molecular formula, each molecule contains 2 carbon, 6 hydrogen, 1 oxygen. So we can have 2 different ways to draw it. You can either have a alcohol. We'll talk about functional group later, but this is an alcohol. Or you have a CH group, CH3, CH2, OH. So that's ethanol. Or you can have that oxygen in the middle, CH3, O, CH3, that's methoxymethane. I'm not going to test you on the IUPAC name for this class, but when we're talking about these names of the molecule, I'll keep talking about it so you're familiar with how to name these molecules. There might exist another possible constitutional isomer for this molecule. And can any of you thinking about what that looks like? Or never mind, I got it wrong. There's only 2. So it's okay. All right, so that's the end of all my material of today. Do we have any questions? All right.